Morning, everyone. Welcome to lecture 33. And let us continue with a joint continuous random variable. So let x and y be two continuous random variable. And we define the following. The conditional PDF can be defined as we did in the joint discrete case, but it's, yeah, so it's fxy, the joint, and then divided by the marginal. And then conditional probability, given that x is in A, that x belongs to A, given y equals to y is given by this. So we need a conditional PDF now, okay? And then we integrate it over the domain of x, okay? And then conditional CDF of x given y equals to y is denoted by this, and this is probability that x is less than equal to x given y is equal to y, okay? And then we put the limits for x, so which is minus infinity to x, okay? And then we put the conditional PDF of x given y. So these are the definitions of conditional PDF, conditional probability, and conditional CDF. Okay, so we will try to see these some examples. So let x and y be two jointly continuous random variables with joint PDF, which is given by this. Then for y greater than equal to 0, less than equal to 2, so this is also the domain here. Find the following: the conditional PDF of x given y equals to y, and the conditional probability. Okay, so we are going to use the definition from that we just showed. Okay, so the conditional PDF of x given y equals to y, and then the probabilities. Okay, so for the conditional PDF of x given y is equal to y, what we are asking for is this. Okay, so x given y, and yeah, so the definition for this, if we look back, then this is this. So joint divided by the marginal, right? So we need that. So this is fxy, xy divided with the marginal. This is y here, okay? So this is what we need. So this is something we are given already, which is here. What we don't have is this this marginal. So we are supposed to find this marginal now. Okay, so let us find this fyy. So we find the marginal PDF of y, and this is denoted by fyy, and this is 0 to 1, and x squared by 4, y squared by 5, xy by 6, right? So x squared by 4 plus y squared by 4 plus xy by 6, and since I need marginal with respect to y, I need to integrate out x. Okay, so this will be so here the integration we have to do. So this is x3 by 3 times 4 plus y square x by 4 plus x square y by 2 times 6. Okay, so and then we have to put this integration limits between 0 and 1. Okay, so if we calculate this out, so what we'll have, so x cubed by 12 plus, so we are putting the limits for yeah, okay, so we are putting the limits for x, right? So this is 1 over 12 plus y square by 4 plus y by 12. Okay, so this will be 3y square plus y plus 1 by 12. Okay, and all this is for the valid range of y. This was already given to us. So this marginal we found, and then our goal was to find the conditional. And this was given by fxy xy divided by the marginal fyy. Now the joint we are given, right? So the joint we were given to be have this, right? So so we will substitute that here. Okay, so we have x squared by 4, y squared by 5, xy by 6, x squared by 4 plus y squared by 5 plus xy by 6, and then divided by fyy. Fyy is this guy. Okay, so it's 3y squared plus y plus 1. Okay, divided by 12. Okay, so now if we simplify this further, okay, so if we simplify this further, then what we are supposed to get? Simplify this further, right? So here, what should be the proper thing to pick here, right? So 210. Yeah, we can just multiply this out. It doesn't matter, right? So 4 times 5 times 6. We need to take the LCM actually. So 30 x square plus 5, so 24 y square plus, so 20 xy divided by 3y square plus y plus 1 divided by 12. Okay, so this 6 goes here, and then the 2 here, and then the 12 goes with the 10 is there, right? Okay, so 10, and then yeah, so 10 is there, 30x squared plus 24y squared plus 20xy by 10 divided by yeah, 3y squared plus y plus 1. Okay, so yeah, so some expression here we get, and then for yeah, so this is the marginal. Okay, so you can compute this, and then the next question was, so this is done. Next question was probability that x less than half and y equal to 2. So this is the B part, probability that x less than half and y is equal to y. Okay, so y is equal to y. Now this, so according to the definition, so we have to put the range of x. The range of x is lower bound of x is 0 anyway, and upper bound is defined by the condition itself. So the condition is half here. So this is 0 to half. Okay, and then the x and the conditional. The conditional we have, because we are trying to compute this probability for the conditional, so we have to put the conditional here, and then we have to put the dx here. Okay, now this is found before, okay, already, so we can just substitute this and then put the limits, integrate and put the limits. Okay, so so these were the two things we were supposed to find. Okay, and this may like come out as a function of y. Okay, so this output is a function of y, is a function of y, because we are only integrating with respect to x, so y will remain like a constant, but so overall this is a function of y that you will see, okay, after integrating. Okay, so now let us define, so what we have done so far is conditional f, conditional probability, and now let us define conditional expectation and conditional variance. Okay, this is something we have seen also in the discrete case. Now let us do this in the continuous case. So expected value of x given y equal to y. So this is the conditional expectation we are interested in. So this is expectation of x given y equals to y. This is just x times the conditional PDF you have to just put in there. Okay, and then integrate from minus infinity to infinity, or the valid range of x. And conditional expectation of the function of the random variable. Similarly, we can extend this idea to function of the random variable. This was just random variable, here is function of random variable. So in place of x, now you have gx here, and then you just put the conditional PDF here only. Okay, so this is conditional PDF. You don't have to put f of gx given y or something like that. You don't have to do that. You just have to put conditional PDF here and then gx here, and then integrate this. Conditional variance of x given y equal to y is again extended as before. So we have expectation of the x squared given y, and then minus expectation of x given y whole squared. Okay, and given that these things are defined for continuous case, you just have to substitute those values here. Okay, so let us see some solved example. Let x, y be two jointly continuous random variable with joint PDF given by this. Okay, so this is like same example as before. So find the following, find the conditional expectation, okay, and find the variance of x given y equals to 1. Okay, so let us see how we can find this. So before, like we have found, yeah, so we are supposed to find expectation of x given y equals to 1. Expectation of x given y is equal to 1. Okay, so this, if we write down, then this is minus infinity to infinity, and x, and then the conditional expectation of x given y, and then dx, right? So this is already found. Okay, so this is already found, so you can just substitute these values, but only thing is, like, you can check the range of x is 0 to 1. So you can modify this range to now 0 to 1, and then f x given y dx. So you just need to now integrate this. Okay. Yeah. And one more thing is, since y is given to be 1, right? So you have to make sure that it is evaluated at a y equals to 1. So this is like evaluated at y equals to 1. Okay, so here in place of y, you have to put 1, and then it becomes a function of x, and then you integrate in the range 0 to 1. Okay, so if we would have gone further and simplified this, then x given y, the conditional would have come out to be 3x square plus okay, or rather we have to put everything, right? So only thing is, like, the 10 factor seems to be going away, and this 24 is correct here. Okay, let's see, 24, yeah, 424, yeah, that's fine. Yeah, everything seems fine, right? Okay, yeah, so anyway, like, we have to, like, substitute these values here, and then yeah, so here you substitute these values here, and then you can integrate this out. Okay, so I don't have to go for all the detail here, and then for the variance, so the conditional variance we want, right? So variance of x given y equals to 1. Okay, so variance of x given y equals to 1. So for this we need, what was the formula? X square given y is equal to 1 minus expectation of x given y whole y equals to 1. Okay, whole square. So so only thing we need is this guy. So expectation of x square given y equals to 1. This is not something we have not computed yet. So this will be minus infinity to infinity x square f x given y x given y. Okay, that's it, dx. And this will, since we are integrating with respect to x, so the valid range is this, x given y, and then x given y dx. Okay, so you can integrate this, and once you have this, then you have this, and then you have this from here. So you can do the further calculation here. Now, in the case of also continuous random variable, we can also define independence of two random variables. So two random variables, continuous random variables are independent if the joint can be written as the product of the marginals, or equivalently, we can also write that the joint CDF can be written as a product of the marginal CDF. So if x and y are independent, it's an easy thing to establish that that expectation of the product will be the product of the expectation, and then the expectation of the product of the functions of the random variable will be expectation of the product of the expectation of the functions of the random variables, right? So these are the things you can easily verify. You can easily verify this. Okay, so I'm leaving this. So if we are given joint PDF of x and y, and if we can write the joint like this, then also we can claim that they are independent. So I mean, that's how we have defined it anyway. Okay, so so the idea here is like, given a joint, can you find a function somehow that can be written that I can split like this? Okay, then I can immediately claim that fxy is, because so what I'm trying to say is like, it does not have to be only product of the marginal. You just produce two f1 and f2, okay, and which only depends on x, another one only depends on y. If I multiply, I should get back this. Okay, so then like we can also claim that x and y are independent. Okay, so let us see an example of independence. So let us consider this joint PDF. So there are like two cases, joint PDFs given to us. So are they independent? Like, can I write this? Obviously, these limits also have to be taken into account when you are writing the product, right? So the product should be valid. So for the joint PDF, what we are asking for is it can be written in the terms of marginal, right? But and then these limits have to be also taken into consideration. So let us now see if we could write this as a product of the marginals, right? So we are supposed to find the marginal, and then we are supposed to check whether I can write this as a marginal. So let us find the marginal, right? So what is the definition of the marginal? So let us compute the marginal. Compute the marginals. In this case, we have fxx and fyy as we are supposed to find. So 2e to the minus x minus 2y, right? So marginal will be fxx will be, now we will out over y, right? So y lower bound is 0, so 0 to infinity, and then 2e to the minus x minus 2y, 2e to the minus x minus 2y, and then since we are computing marginal with respect to x, we are integrating with respect to y. So since we are integrating with respect to y, 2e to the minus x is a constant. So this is 0 to infinity, e to the minus 2y. This is 2e to the minus x and e to the minus 2y by minus 2. That's the integration of that. And this is 2 gets cancelled. Okay, so this is like I take minus also come out, so e to the minus x, and this is like infinity, so 0 minus 1, right? So this is like minus 1, so this is e to the minus x. Now we compute the marginal fy. We also need to compute this. So x lower bound is 0, so I can put 0 and then goes to infinity, and then the joint is e to the minus x minus 2y, and then now we have to integrate with respect to x, so 2e to the minus 2y, 0 to infinity, and what is left inside is e to the minus x dx. So this is 2e to the minus 2y, and then the integration is minus x minus 1, 0 to infinity, and then this is minus 2 e to the minus 2y, and e to the minus x 0 to infinity. So this is, so again -1. So this is like 2 e to the minus 2y. So if we now, this implies that fx x and fy y. So if you see fx x is this and fy y is this guy. So if I multiply this, I do get the joint. So this is fxy xy, right? So 2 e to the minus x minus 2y, right? So I do get the joint. So this implies that that x and y in the first case is independent. Okay, and then now we need to check the second case. So for the second case, fxx is, so this is at 8xy. Now we are computing fxx, right? So fxx, so we have to do the integration with respect to y. So we have to take the limit of the y. Take limit of y. So limit of y is lower bounded by x. Okay, and upper bounded by 1. So x to 1. So this is x to 1. And then the joint was at xy, right? So this is the at xy, 8xy. So we are integrating with respect to y. Okay, so 8x is a constant, it comes out. And this is y square by 2. And the limits are x to 1. So this is 4x y square x1. So this is 4x. Okay, so we put 1 here, and then minus yeah, so we put 1 here. Okay, and so this is like 1 minus x square, right? Yeah, so this seems to be like 1 minus x square. Yeah, it seems correct, right? Okay, and fyy is, okay, fyy, so we need to look for x ranges, right? So x is ranged from 0 to y, right? So x will range from 0 to y, 8xy dx now. Okay, so this will be equal to, so we are integrating with respect to x, so 8y comes out, 0 to y, and x dx. So this is 8y x square by 2, 0 y. So this is 4y cube, right? So here fxx times fyy is not equal to fxy xy. This implies xy are not independent. Okay, so this is the case where we saw they are not independent. Okay, so remember that you may be tempted to say that this can be split in the sense that I can write x and then y, right? But then like this range also plays a role. Okay, it is because of this these bounds on x and y, it did not become independent. Okay, here it was okay, because okay, when you see a dependence of x on y and so on in the range, then it may not be the case that they can be split as a marginal. Okay, so here you could write this as some two functions, but then this has an important role to play. Here I could have also immediately identified this as 2e to the minus x and then e to the minus 2y. Okay, so here it did came out to be like the product of the marginal. So what I'm trying to say is like it's important that you actually compute the marginals. Okay, that's a safe, because you may not understand what role these limits may play in the splitting of these functions as a product of two single variable functions. So it's always safe that I do the marginal and then check the product of the marginal, it's equal to this or not, because the ranges change these limits and so on. Okay, and hence it may not be be equal to the joint. Okay. Consider another example where we choose a point xy uniformly at random. Okay, so from the following disk. So you know what is this now. Okay, so this is a circle. Okay, and center at 1, radius is 1, center at 0, and the area of this will be pi, right? Area is pi. Okay, pi is r square, but r is 1. Okay. The joint PDF is given to us, so it takes the constant value in this disk. So find the constant C and find the marginal PDFs fx and fy, and find the conditional PDF of x given y, where y is given to be in this range. Obviously, because it's in a circle. Okay, so let us try to. And then another question is like, are x and y independent? So this is like one more question on independent random variables. Okay, so to find the constant C, what will you do? Right, to find the constant C, what property I'm going to use? Well, I know that the integration of this PDF over the whole defined range, in this case it's D, is going to be 1. Okay, so then I know what to do to find the constant, right? So to find the constant, we have that. So the first part of the question is to find the constant. So we have, so what we have is minus infinity to infinity, minus infinity to infinity. What we know is that joint PDF, since it is a PDF, it must be equal to 1. So this implies, so but this integration reduces to the disk, and then the PDF value was C dx dy. This must be equal to 1, but C comes out, and the integration of this disk will be the area of the disk, which is pi r square, which is pi, r is 1. So this is like C pi is equal to 1. So this implies C is equal to 1 over pi. Okay, the constant is found. Now the next question is find the marginal PDFs fxx and fyy. Okay, so the marginal PDF fxx, right? So if I want to find fxx, then what do I know is that I have to do the integration minus infinity to infinity of fxy xy, and since I'm computing margin with respect to x, I have to put y here. Okay, and I know that it was C, and C was 1 over pi. Okay, and y range I know is from it depends on x, right? So the y depends on x. So this is the circle we have, and y depends on x, right? So this is the reason x square plus y square is less than or equal to 1, right? So y range is plus square root of 1 minus x square and minus square root of 1 minus x square. So this is the range of y we are given. So that's something you have to substitute here, right? So minus 1 minus x square and 1 minus x square, and c, so 1 over pi was here, right? And then this is dy, and if we integrate this out, because this is a constant, so this minus this will be 2 square root of 1 minus x square by pi. Okay, so this is the margin with respect to x, and then similarly by symmetry, so y is nothing different and nothing is very similar. Similarly by symmetry, so by symmetry we can say that fyy is 2 1 minus now y squared by pi. Okay, so the marginal also we got. Now we have to find the conditional PDF of x given y, where y is between this. So conditional PDF of x given y. So conditional PDF, what was the definition that we just note down? So this is given by the joint xy divided by the marginal, and since condition is on y, we divide by y. Okay, so we have the joint, we have found the marginal just now. So it's a matter of like taking the ratio, right? Okay, so the third one is, so we know that fx given y, x y is the joint xy x comma y divided by fyy. Okay, and fxy was 1 over pi, right? So fxy was 1 over pi. It was c, which was 1 over pi. So this is 1 over pi, and fyy is 2 square root of 1 minus y square, 2 square root of 1 minus y square divided by pi, right? Okay, so pi goes away. So this is 1 by 2 square root of 1 minus y square. And obviously y has the restriction that, I mean, yeah, so okay, let us like summarize this. So this is so hence fxy x given y is a function of y. Obviously, we always know that this condition is a function of y. So this is 1 by 2 square root of 1 minus y square, and we know that the rest, and these are for the values of x. Okay, so these are defined for the values of x, and the values of x it is defined for is minus square root of 1 minus y square less than equal to 1 minus y square plus 1 minus y square. Okay, and then this is 0 otherwise. Okay, so this is the conditional that we were supposed to find. And are x and y independent? So for so one more thing we noticed from here, what do we notice from here is, what is this distribution, right? Can you identify this distribution? Like it is taking this form, right? So what kind of distribution is this following, this conditional? Okay, can you guess what is this distribution? This is uniform, right? EB and then 1 by B minus A form, right? So this is the distribution. So note that given y is equal to y, x is uniformly distributed. It distributed on the interval minus square root of 1 minus y square and 1 minus y square, right? In other words, in our notations that we have defined, y is equal to y is uniform minus square root of 1 minus y square and square root of 1 minus y square. Okay, so this is how we write. Okay, so so we have this. This is turns out that it's a uniform. Are x and y independent? So are x and y independent, right? So to do that, we have already computed the marginals, and it doesn't seem to be the case, right? Because is it that the product of the marginal is giving me the joint, right? So it is clearly not, because fxx is this and fyy is this, right? So the fourth one, because okay. Now we have something called, these are extensions of what we have done in the discrete case. So we have something called law of total probability now. Now law of total probability, if you recall, what was the law of total probability? What we do is, like, if we compute the probability of an event A, we find a partition of the set sample space. Okay, so Bi is partition of sample space. In other words, pairwise disjoint, and union is this. So what we know is, like, this is this can be written as a summation of P of A given Bi, probability of Bi. Okay, let us say Bi's are from 1 to k. Okay, so this is something we know, law of total probability, and these are just extensions of these things. Okay, in the continuous case, because we know how to compute this conditional probability in the continuous case, we know probability of an event in the continuous case, and so on. So this, now we, instead of summation here, Only thing that we have to do is to change to integral, and then this PMF changes to PDF in the continuous case. Okay, so probability of the probability of A given BI, and then probability of BI. Okay, so this we can write this as probability of A, which eventually will be computed again using conditional CDF and PDF and so on, right? Okay, so this is how we will define this: the condition on X and then PDF of X. Okay, so law of total expectation. So law of total expectation is again the extension of the discrete case. We have conditions as before, but in this case, let us say we are computing expectation of Y, and then we are conditioning on X. So Y given X, and then PDF of X. Okay, and this, in other words, can be written also like this. Okay, this is expectation of Y given X. Okay, so if we can, so in some cases it may be easier for you to compute this. Okay, your goal is to compute expectation of Y, but it may happen that this thing is easier because Y given X is a well-known distribution to you, and then for that expectation is known. For example, Y given X is given to be exponential. Then the expectation of Y given X will be exponential of lambda. Then this will be lambda, right? And then expectation of constant will be just lambda. So in cases where Y given X is easier for you, you may want to use this. Okay, but if not, then you can go with the usual definition. But in this case, if you want to compute, you need to compute this. And for this, you do need the conditional PDF X given Y. Okay, so you may need a conditional PDF, so that may be given to you as well. Okay, so this is law of total expectation, and law of total variance. It's kind of interesting. You just flip the expectation and variance. Okay, so expect variance of Y given plus variance of the expectation of Y given X. Okay, so this is something you can memorize this. Okay, so this is how these are defined: law of total probability, law of total expectation, law of total variance. Now let us see an example. It's always good to see things with an example. So let us say we have two independent uniform distributions, and we are supposed to find probability that X cubed plus Y greater than 1. So the idea that I'm going to use is, sometimes it's easier for me to use the law of total probability. When I'm interested in law of total probability is when, especially when independent random variables are given to me. Because if the independent random variables are given to me, then this thing will just go away. The conditional will go away, because if A and X are independent, then probability A given X will be just probability of A. Okay, so if something is given to me already like that, so in this case, X and Y already see and hint that they are independent and uniform, and I'm supposed to do this. So if I use the law of total probability with the conditioning I do on X, okay, then I can have something here. So let us see a solution for this. So we are supposed to find X cubed plus Y is greater than 1. And we use law of total probability. So this will be minus infinity to infinity probability that X cubed plus Y is greater than 1 given X is equal to X. Okay, and fxx dx. X, remember, is a uniform in 0, 1. Okay, so these guys are well known. Okay, and so X cubed plus Y here. Okay, X cubed plus Y is greater than 1. Okay, so this is using law of total probability. Okay, and now what can I do here now, right? So so this is what we have, and X is given to be X, right? So this will reduce to, and then the limit also we are doing X, right? So X is a uniform between 0 and 1. So this will go from 0 to 1 now, and this will reduce to probability that that x cube small x, right? So small x cube plus y is greater than 1 given x is equal to x, fx x dx, right? So this is like some function of y because x is like, okay, and so and then y, and so from here, like I can solve for like y is greater than 1 minus x cube and so on. Okay, so due to independence of x and y, I can just write this as 0 to 1 probability that y greater than 1 minus x cube, fx dx is 1 times dx. Okay, and this is y is uniform, but then this is greater than. So what I need is, so I can make this less than equal to by doing 1 minus. So this is 0 to 1 and 1 minus probability that y is less than equal to 1 minus x cube dx, and this is like uniform, right? So the CDF, so this is like the CDF of the uniform distribution, right? So CDF of the uniform distribution is this, the same guy, right? So this is like 0 to 1, 1 minus x cube dx, right? So this is like x cube, 1 gets cancelled. So x to the 4 by 4, x to the 4 by 4, 0 to 1, and this is 1 over 4. Okay, and this is because y is uniform. Okay, because y is uniform, 0 to 1. Okay, so we have used the total law of total probability here. Okay, the law of total probability, and then we exploited the fact that they are independent. So this x equals to x go away, right? So probability that x given y will be probability of just x, right? If x and y are independent, x, y independent, then this is the thing we know. So this went away because of independence. Okay, so this is where because x, y are independent. Okay, so that's why I got rid of this, and then I have just y greater than 1 minus x cube from here, and then this was just 1 because this is the uniform. So this was 1 because x is uniform, 0, 1. Okay, so all this is being used, and then we can solve for this. So here, when I'm given like two independent, right? So I may think about using total probability because it's a bit simpler. Okay, it's a bit simpler to compute this. Okay. Now let us see some more examples. Let x be uniform, and for given x equal is given to be exponential with parameter lambda equal to x. So in other words, what we are given is this: y given x equal to x is exponential, or if you can generalize for any x, because this is true for any x, so then I can also write y given x is exponential of capital X. So what we are told to find is find expectation of y and find variance of y. Okay, so so what is the problem in hand? The problem in hand is we are supposed to find expectation of y, right? But the information that we have in hand is the conditional is known. Okay, and we are supposed to find the expectation of y, and these are the places where you should invoke the definition of law of total probability, because you have information on the conditional, because law of total probability, law of total expectation requires this, right? And this is given to you in this case, so it's better to do use that. Okay, so it's better to use so what was the law? So now the question is, what was the law of total expectation, right? So let us write down the law of total expectation. So let us say the first one is find expectation of y. This is what we are supposed to find. Now, by definition, what we know is that this is minus infinity to infinity. this is expectation of the conditional, right? So y given x is equal to x, and then the PDF of x dx. So this is using by law of total expectation. Okay, so this is the definition that I just introduced, and now we are trying to use this, right? Now y given x is equal to x is known to us. This was exponential, right? And the limits of x we want, right? So we have to look into which variable you are integrating with. The limit of x is uniform, right? So this is like 1 to 2. So 1 to 2, and yeah, let us write one more time. So y given x is equal to x, and then it is uniform, right? So uniform, the fx will be just 1 dx, right? So like b minus a, right? Okay. So okay, and what is this now, right? So we are given that y given x equals to x, we are given, right? So this is exponential of x, right? So this is exponential of x, and then expectation of the exponential distribution is so expectation of this exponential distribution will be just 1 over x in this case, right? So this will be 1 over x. This is what is given to us. Okay, so this is exponential of x, so the expectation of that will be 1 over x. Okay, expectation of the parameter lambda will be 1 over lambda, right? This is what we know for the exponential, right? Okay, so and then we have 1 to 2 and dx, right? So this is log 2 log x, so log 2 minus log 1 is 0, right? So this is just ln 2. Okay, another way we could have found this is by using the fact that expectation of y is expectation of y given x. Okay, so this is an identity we are familiar with. This is also law of iterated expectation, if you can recall. So in this case, I would prefer to use this because I don't know much about y directly, but what I know is y given x I know. So y given x I know is exponential, so expectation of that will be 1 over x, right? So expectation of that will be 1 over x. So this will be expectation of 1 over or capital X. Okay. So expectation of 1 over x, and then now I know that x is a uniform. Okay. So the PDF will be the same thing. Okay. So the PDF will be so this is so I can integrate this, right? So this is like expectation of the function of the random variable, right? So this is like 1 over x, and then f x, right? So this is how we compute the expectation of and then x lies between 1 and 2, right? And this being uniform is just 1. So this is 1 to 2, 1 over x dx, which again turns out to be ln 2. So in this case, this helped us. Okay. Now we are supposed to find the variance of y. Again, we don't know y explicitly, but what we know is y given x is known to us, and that might be useful for us. Okay. So one possibility is that you might you may want to compute this directly. So this is like expectation of y whole squared. Okay. Okay. But then, yeah, so you have to like explicitly compute these values, right? So rather what we would like to use is we would prefer to use the law of total variance, right? So law of total variance, according to that, will be expectation of the variance of y given x plus variance of expectation of y given x. Okay. So this is the law of total variance. Okay. So law of total variance. So if we have that, then we can write this now. Okay. So what do we have now? So variance of y given x. What could be the variance of y given x? Now y given x is known to be exponential, right? So that we know is that for exponential, it's 1 over lambda, exponential of lambda, the variance of that is 1 over lambda square, right? So that we know. So this is 1 over x square, and then expectation of that. Okay. So now let us do this here. So we have variance of y, which is, so in this case, variance of y given x. This is variance of the exponential of x. This is 1 over x square. So this is exponential of 1 over x square. Okay, I mean the capital X square plus variance of expectation, and variance of expectation is 1 over x for exponential. So this is exponential of 1 over x square plus variance of this is, the usual definition of this is 1 by x square minus expectation of 1 over x whole square, right? So this is expectation of 2 by x square, so due to linearity of expectation, and then this is something we have computed before. So this was a natural logarithm 2, then squared. Okay, and then we are supposed to find this value, right? So this is x is like uniform here, right? So x was given to be uniform, so we can compute this this using the uniform, right? So like I will just leave it. So the limit is 1 to 2 is 2 by x square, and then PDF of x dx, right? So if you integrate this out, then you can get some value, and then you can substitute there to get to solve the problem, right? Just like before, we can also have expectation of function of two random variable in the continuous case. So in this case, it's again a straightforward extension. So just put gxy and then the joint PDF x and y. So in this case, let us see an example of expectation of function of random variable. So this is the joint PDF given to us, and then we are given a function of, so this is like expectation of g of xy. Okay, so we can compute this. So here, okay, let me do it here only. Okay, so this is expectation of xy square by definition minus infinity to infinity minus infinity to infinity xy square fxy xy dx dy. So this x and y are going from 0 to 1. Okay, and they are independently going from 0 to 1. They don't depend on each other. Okay, so x and y, and then this is xy square, and then fxy in this region is x plus y, and then dx dy. And if you integrate this out, then this is 0 to 1, 0 to 1. So overall, this is like x square y square plus xy cube and dx dy. So if you integrate this out, then this is 0 to 1, x3 by 3, and y first I do with x3 by 3, and then x square by 2, and then I put 1. So I will be left with y square plus y square by 3 plus y cube by 3. Okay, so y square by 3 plus y cube by 3 dy, and if we do this, then we get some value here. Okay, so and then another question could be, what do I how do I find the CDF of function of two random variable? Okay, so previously we saw PDF of function of two random variable. Now we are CDF. Now for the CDF, yes, so what we know from definition is that the z is a function of x and y. So I just start from here, fz z. This is z less than equal to z by definition. So in place of z, I put g x y. This is less than equal to z. And now Now this thing, the probability that this is less than or equal to z, this is giving me some region where this is defined, right? So that region is denoted by d here. Let us say the region of integration, right? Okay, that will be found from here, and then possible ranges for x and y will determine this region, and then I will just put the PDF of xy. Okay, join PDF xy, and so this is the region that I'm talking about, and this limits will involve x and y, because this guy is not having any thing to do with z here, right? So the z will appear somewhere here. Okay, so because x will less than or equal to some z function of z and so on, right? So these limits will be defined by the z. So that's why the output of this you will see will be in terms of z. That is what we are expecting. Okay, so these limits are important here, which are functions of z. Okay, and then hence you get finally everything in terms of z. And to compute the PDF after that, I know very well that I can just differentiate this. Okay, so I differentiate this with respect to z, obviously, because this is a function of z, so I just differentiate it with respect to z. Okay, now let us see an example for this. So this is like x and y uniform, and z is x times y. Find CDF and PDF of z. Okay, I think I'm running out of time now. It's 10:27, so I will stop here. I'm almost done with this continuous PDF, and then I will go to the covariance and correlations, and then multiple random variables in the next class. Yeah, so I hope most of you are doing the poll for the quiz, okay, the midsem quiz, which is now postponed to much later now. So I hope you will do the polling and settle down on some time. Okay, so I think I'll stop here. If you have doubts, do ask me. Okay, currently most of you are not asking any doubts, so I don't know what is going on. Okay, so I will stop here. Okay, bye.